fabricating materials atom by atom, improving cancer drug efficiency up to 50%, and developing solar cells that function like a moth's eye. Just a few examples of the emerging science of nanotechnology.
Emerging Science is a Vermont Public Television production in partnership with and funded by Vermont NSF EPSCoR. EPSCoR, supporting science and engineering in Vermont colleges and businesses and encouraging young Vermonters to seek careers in science.
Hi, I'm Amy Seidel, and welcome to Emerging Science, a program that highlights research starting here in Vermont. This week, we're exploring nanotechnology. We're going to see how Vermont scientists are creating satellite propulsion systems that fit in the palm of your hand, how they're condensing the equipment of entire medical laboratories to something that sits on the tip of your tongue. We'll see this and a lot more as we explore the world of nanotechnology. But first, what is a nanometer? A nanometer is 1/1000th of a meter. That's 10 to the minus 9 meters. It's roughly 1,000th the size of a human hair. Let's start by taking a quick look at the history of nanotechnology.
To go way, way back, you can go back to things like the art and technology of making like stained glass. It turns out that the stained glass that they made centuries ago, the color came from certain metals that they put in the glass. Some of those colors actually come from the metals clumping up into nanoparticles and interacting with light. So there are examples in history where nanotechnology happened by accident. In the modern era, a good place to start would be in the 1930s with the development of the electron microscope. So the electron microscope, for the first time, gave us the capability to actually go down and see things that are smaller than what you can see with visible light. In 1959, the physicist Richard Feynman gave a lecture called "There's Plenty of Room at the Bottom." He had two ideas. One was making a very small motor, perhaps the beginning of some kind of machine. And the other one, which I think was at that time the more powerful idea, he imagined, for example, writing the entire Encyclopedia Britannica on the head of a pen. Before about 1960, the electronics companies only manufactured individual switches. It was just about that time that the first what we call integrated circuits came into being, where the switches were already hooked together so that you could make something like a computer chip that was a complete device. Even though it didn't begin as a nanotechnology, that was the beginning of what is now a very well-developed nanotechnology, which is the computer industry.
In 1981, the scanning tunneling microscope was invented, allowing for the first time the imaging of individual atoms. The buckyball, a cluster of 60 carbon atoms, was discovered by researchers at Rice University in 1985. Named after Buckminster Fuller and resembling his famous geodesic dome, it set the stage for nanotechnology. In 1986, Eric Drexler expanded on Feynman's theories in his book Engines of Creation. When Don Eigler spelled IBM with 35 xenon atoms, atomic manipulation was born.
But nevertheless, the idea and the challenge is still there of can you get down on a nanoscale level and build things at that level? And how well can you direct those kinds of processes?
Chemists have traditionally worked using bottom-up techniques, meaning they combine molecular materials to form new nano-sized materials. Today, as Richard Feynman suggested back in 1959, scientists and engineers are constructing things at the atomic level, from top down. They are actually fabricating molecular-sized objects. When things get to be that small, their physical and chemical properties change. They actually behave radically different than the same materials at a larger scale. This is because nanomaterials have a very large surface area. To visualize this, we have a smooth apple. We also have an object of the same size with a fibrous exterior. Two objects the same size but very different surface areas. For that reason, we'll see how nanomaterials behave very differently.
Meter square per gram is a way to monitor the surface area of a material. So if you pulled a piece of brick out of the wall, the surface area might be 10, 20, or 30 meters squared per gram. And that's about standard for a normal material every day. And the things that we make have surface areas of 1,000, 1,500 meters squared per gram. So there are many, many times more surface that you can use to do reactions. Just this idea of extra volume and extra porosity, extra surface area inside.
When you have that large surface area, a chemical catalyst, the effort to make a chemical reaction go forward, to push a chemical reaction forward, when you have that large surface area per mass of material, you can make chemical reactions happen that normally would not happen.
Darren Hitt, associate professor in UVM's mechanical engineering program, has a need for just such a chemical catalyst. He is developing thrusters for nanosatellites, enabling them to steer in space.
A typical satellite is quite large, maybe the size of an oil drum, sometimes as big as a school bus. What we're talking about by the term nanosat is actually a greatly reduced satellite, something that's roughly the size of maybe a birthday cake that weighs, perhaps 10 kilograms. The dynamics and control of nanosats is a huge research area. We're focused solely on the propulsion system, and the challenge here is to miniaturize the propulsion system for the satellite. How do you precisely deliver a very minute level of thrust? Thrusters are typically a monopropellant scheme. This is not a combustion process. Rather, this is what we call a chemical decomposition process. You take a fuel, you expose it to a catalytic material, and chemically it becomes unstable and decomposes. And in that process, for a monopropellant, there's a lot of heat energy that's released, and what we do is we leverage that heat release and convert that into thrust and kinetic energy for the satellite. Traditional catalytic beds have been constructed of so-called packed bed catalysts. That imagine a soda can filled with pebbles or powder or granules of a catalytic material. And wherever the fuel comes in contact with the surface, it decomposes. Great configuration, worked for decades on spacecraft. The problem is it's very, very difficult to produce the equivalent on the microscale. We've drastically reduced the volume of the catalytic chamber. Now we're talking about something 10 microns deep or less. And what we're filling this with are so-called nanorods of ruthenium oxide. These are being grown by Professor Walter Varhue in electrical engineering.
Well, you know, that's the weird thing about it. They just grow by themselves. You create the situation where they will form, and they even use the word self-assembly.
A silicon wafer is prepped and loaded into a vacuum chamber. The wafer is transferred to the main chamber and heated to 500 degrees centigrade. A piece of ruthenium has been positioned in the chamber. Its molecules are shaken loose by argon gas. As the ruthenium drifts through the vacuum, it comes into contact with pure oxygen that has also been introduced. Now, ruthenium oxide is formed and adheres to the silicon wafer, forming the desired nanomaterial. Professor Varhue's nanomaterials are providing the fuel catalyst for these tiny thrusters for Darren Hitt's nanosatellites. He's also using his nanomaterials for applications in the field of renewable energy. He predicts that nanomaterials will be the key to using the sun's energy to form hydrogen in a hydrogen-based economy.
If you could use the sun's energy, which is falling on the surface of the Earth anyways, and then collect the hydrogen that's produced, just splitting water, then you could put it in your automobile. You can run generating facilities with a fuel cell. It would be clean, cheap energy. energy from the sun travels here as photons. It's a quantized packet of energy. Average energy of that spectrum is 1.5 electron volts. How much energy would it take to take one water molecule and split it in half? It would take 1.23 electron volts. So on average, there's enough energy in a photon from the sun to break up a water molecule into useful hydrogen and oxygen. So the energy is there, just have to figure out a way to use it. Well, the hydrogen economy is what you hope to go for. So now what do we have? We have the petroleum economy. We have to go to the Middle East and get their oil. On another perspective, this whole concept of global warming, having greenhouse gases emitted into the atmosphere, is going to cause us and the rest of the world problems. So if we can avoid that problem, as a scientist or as a father, I have to feel good about that.
Another way to harvest the sun's energy is with the existing technology of photovoltaic. Bill Parker of Creative Microsystems in Waitsfield is working on increasing efficiency of solar panels. And to do this, he's turning to the examples that nature provides. In this case, he's mimicking the function of a moth's eye.
When you have a solar panel, I say, on a roof of a building, the sun doesn't stand still. Obviously, it's moving throughout the day. Our piece of the puzzle is how to get more light into the solar cell. Our immediate goal is to understand from what nature has done how to control light in ways that are seen in nanoscale structures in biological organisms. And one of those is the eye of a moth. The moth's eye is a really elegant optical instrument. We have a retina and a single lens. The way that a moth's eye is built is that it has many lenses and many nerves that then combine individual images. These are extremely minute nanometer scale bumps over the surface of its eye that act to let light be more